So let me first introduce myself. My name is Harald Karg. I'm a geologist and basin modeler at Saudi Aramco. And this is my first participation to the Global Heat Flow Day. So thanks everybody for having me here. Thanks especially to Sven Fuchs and his co-organizers for inviting me, and to all of you for having me in this event and giving me the opportunity to speak. Over the next probably 25, 30 minutes, I will talk about heat flow on the Arabian plate. So essentially, title is Terrestrial Heat Flow on the Arabian Plate. And I bring new thermal data, insights from the interpretation and analysis of new thermal data, and present you results of our thermal modeling in order to constrain surface heat flow on the Arabian Plate. When I saw your background image the whole day already, I was actually quite delighted to see this nice globe with the projected surface heat flow on top of it. And I was obviously curious how Saudi Arabia sticks out on that picture. And if you look at that closely, Saudi Arabia, and I think, or the Arabian Plate in general, has always been known as a rather cold regime, as rather cold plate. And actually, this is how it shows up on your background picture here. It's all in blue. And this is partially because the published thermal data on the Arabian Plate, except some tectonically hot provinces like the Red Sea in particular, or the Gulf of Aden, is very, very scarce. There's hardly any published data so far. There's some old data from the 80s, heat flow data, but that's by far not enough in order to unravel a detailed picture of the heat flow on the Arabian Plate. And the other reason why it shows up mostly in blue is because nearly half of the plate is covered, or is actually represented by the so-called Arabian Shield, which is a Proterozoic basement, a huge Proterozoic basement outcrop representing old crust, and that also has traditionally been assumed to be a relatively thermally cold regime. Now, we brought out a paper in mid-2024, just 1.5 years ago, on the effect of Precambrian basement structure on the heat flow distribution in Eastern Arabia. And today, actually, I can show you more data. So since we brought out that paper, we collected more data, especially from the Northern Arabian, Northern Arabian plate. And I will try to give a much more comprehensive overview of the surface heat flow distribution across especially the eastern portion of the plate and the northern part. Not so much the western part, though. So if you look at the geological map of the Arabian Plate, actually, Arabian Plate is one of the, if it's not the smallest, but it's one of the smallest tectonic plates that we know on Earth. And it's squeezed within literally all three main tectonic regimes that we know. So essentially, in the western part, we have the Red Sea portion, the western part, Red Sea, and the southern part, the Gulf of Aden, which are strictly extensional active plate margins. Then as we go to the opposite side in the east, we have exactly the opposite. We have a compressional margin, which culminates in the Zagros fold belt in Iran. And if we go to the north, we have a strike-slip, also an active plate margin with a strike-slip regime, basically a sinistral transform fault system, which we know also as Dead Sea transform fault system. So all three major tectonic elements and forces united in just one small plate. If we look at the plate interior, we can subdivide that into basically two provinces. One in the east, the aforementioned Saudi Arabian or Arabian Shield, which has its mirror on the opposite side of the Red Sea as the Nubian Shield in Eastern Africa. And so that shield, as I said already, is mostly composed of late Proterozoic rocks that are the result of a late Proterozoic amalgamation phase, when that continent or that peninsula has been actually welded together by different tectonic terrains that were bumping into each other's. And that was actually finalized around 600 million years before present. I will come to that in a minute, because that is going to be relevant for my interpretation as to the heat flow in across the plate here. And if we go then towards the eastern half of the plate, we essentially have this massive area which we know as Arabian platform. The Arabian platform, of course, in its deep subsurface is also composed of late Proterozoic basement rocks. However, they have been drilled and penetrated only in very few locations, very few wells. Outcrops do not exist unless we go south to Oman. But on the Eastern Arabian Peninsula, there is no basement outcrop anymore. So it's all covered by sedimentary sections, hosting the most important oil and gas provinces, one of the most important oil and gas provinces in the world that we know present. And sediment thicknesses can be up to 10 kilometers. So also that sedimentary cover plays a major role later on when we try to interpret the thermal field. Those basins, so I put two rectangles here. Those are going to be the focus of my talk today. The central one is the wider so-called Feida and Jafura basin, which is there in the south central part of the plate. And then towards the northwest, we have the so-called Nafud basin. And as you go to the western portion of that Nafud basin, you see those so-called Harad ash-Shamar basalt outcrops. Those are Miocene or Neogene effusive rocks, volcanic rocks that have been extruded during the major activity of the Dead Sea Transform Fault Zone that directly associated with plate tectonism at the northern plate boundary. And we'll also see that those have a major impact on the thermal field in that northern portion of the plate. We come to that at the later stage of the talk. Another interesting feature of the Arabian Peninsula is, if you first look at the left-hand side, is that's a lithospheric cross-section, actually across the from more or less from west to east, according to Stern and Johnson, published in 2010. What you can see is a very stark asymmetry of that plate on a lithosphere scale, especially if you look at the lithosphere-asthenosphere boundary, which is actually getting deeper and deeper as we go to the east. And it's becoming shallower as we approach the Red Sea, which is not surprising. However, if we look at the crust alone, so it's that white, with the black interrupted arrows here, interrupted lines, signature, the crust is more or less homogeneous in thickness. It's not quite true. So actually, if we look closer, we still see magnitudes between the thinnest crust we know is about 32 kilometers in the eastern portion, where we have these sedimentary basins, and up to 42 kilometers. So there's still an oscillation of about an amplitude of about 10 kilometers of crustal thickness. But overall, and compared to the magnitude of thickness change of the entire lithosphere, especially of the asthenosphere, this is very minor in terms of changes. What you see on the right-hand side is a geologic map, simplified geologic map of the entire Arabian Peninsula. And I would like to put draw your attention to these north-south oriented, partially solid, partially dashed lines. Those lines represent so-called basement terrain boundaries, as they have been mapped out and detected through GraphMac work that has been done in the late 90s, 2000s, and deep seismic reflection data, where we can actually map some of those faults. And you see very nicely, most of them are pretty strictly north-south oriented and represent the overall tectonic grain of that plate. And this is actually a relict of what I said earlier, of this terrain amalgamation that happened in the late Proterozoic and was finalized by about 600 million years ago. And the outcrop of those Proterozoic rocks is actually in the Arabian Shield, whereas as you go towards the east, it's all covered by from early Paleozoic to basically Cretaceous and Tertiary sediments. So it's this asymmetry actually a result of the of early Paleozoic extension and thermal subsidence. We'll see basement structure in a second, and we have more than 10 kilometers, up to more than 10 kilometers of sedimentary cover on that. So here is to the left. First, look to the left. There is a basement structure map based on gravity. So this is a gravity field map on the central eastern portion of the Arabian Peninsula. You see here the coastline. You see here the coast of Qatar. Here's Bahrain. This is the Saudi Arabian coastline. And you see also in that gravity field a relatively clear north-south orientation of those features. And I superimposed the deep-seated faults that we mapped out on seismic, and those faults are also, as I said before, strictly north-south oriented and provide overall the structural grain, which is actually starting off from the basement upwards. And that's shown on the right-hand side. You see also these the dashed lines in white, which are the terrain boundaries. Parallel to that, the deep-seated faults and the colors are indicative of the basement depth structure. So you see a very systematic and very strong gradient of deepening of the basement from west to east. And the eastern portion is basically the major Fader Jafurah basin, where we currently have major oil and gas developments ongoing. The central part here, which is called Enala Suture, is, by the way, the structural feature that is associated with the biggest oil fields that we know in the world at the moment, which is Gawar. So all these structural elements have had their impact on hydrocarbon migration, of course, but that's not our topic today. I just wanted to draw your attention to the basement structure here. And this is a map showing magnetics. So this is the magnetization of from magnetics, and you see also a very clear differentiation of the features of the magnetization features between west and east. So you can clearly discriminate the western portion, which has more an irregular, inhomogeneous structure of magnetization, which is our Arabian Shield. And as we go towards the east, we again see that elongate north-south oriented pattern. So reflecting, this is basically strongly indicating or hinting towards the fact that these terrains, these basement terrains that are subcropping here, which are covered by sediments, have different chemical compositions. So this is actually something I would like to point towards as for the conclusions later on. I believe that the different composition of those terrains have a very strong impact on the thermal field of the entire plate. Coming to the model, how did I approach the thermal model here? So I had to simplify, and I discretized the model into 5 layers, essentially. So the uppermost is the sedimentary cover. Then we have an upper crust, a lower crust, and the lithospheric mantle. And the sediments, that's why I said 5 layers. Sediments are subdivided into more carbonate type sediments in the upper portion and more clastic shaly sediments in the lower portion. The implication of that, as you can imagine, has something to do with thermal conductivities, which I assigned. I simplistically and schematized that here on this chart. You see the sediments. K stands for thermal conductivity. Overall, we have thermal conductivities between 2.8 and 3 watt per meter in Kelvin. These are just averages. There are lithologies with significantly lower thermal conductivities like shales, but they are overall not that represented and would not have such a strong impact on the overall average of the thermal conductivity. Radiogenic heat production for the sedimentary cover is also varying quite strongly between 0.4 and 2 microwatt per cubic meter. You might be surprised about the 2 microwatt per cubic meters. It's a lot for sediments. 0.4 is more typical for dolomites and limestones, which we have represented, as I said, in the upper portion of the Arabian carbonate platform, whereas the 1.5 to 2.0 microwatt per cubic meter, we derive those values from spectral gamma ray logs and could empirically back out the radiogenic heat production. Those are representative for the deep clastic rocks that we have of Cambrian, Ordovician, and Silurian age. Sometimes we call them even hot sandstones. We saw sandstones with sandstone layers, not shales, not hot shales, with radiogenic heat production of beyond 2.0 microwatt per cubic meter. Then the upper crust, I think in several discussions and presentations today that was also already highlighted. Upper crust typically has radiogenic heat productions, in our case here, between 9 and 3, also stark variation. I come to that later. In my model, I assumed an increase of radiogenic heat production of the upper crust from west to east, which is partially responsible for the increasing surface heat flow that we will see. We have an average thermal conductivity of 2.5 and a density of 2.75. If we go to the lower crust, obviously much lower thermal radiogenic heat production. Also, that has been discussed today in 1 or 2 presentations. And here I assumed, and I have no data, I have to say, so I had to make assumptions from analogs. I assumed 0.3 microwatts per cubic meter for the lower crust and an average thermal conductivity of 2.5. And then when we go to the lithospheric mantle, same thing. I basically used literature data, a very small radiogenic heat production of 0.02 microwatt per cubic meter, and a relatively high average thermal conductivity of around 4 watt per meter in Kelvin. So the model also assumes, apart from this layering here, a relatively constant overall crustal thickness. And as my model, my software code is basically, it's a commercial software code that I'm using. And the interest that I have as a basin modeler is not only working on the static present day thermal field and heat flow distribution. I'm also interested in the heat flow history of our sedimentary basins, because obviously that has a strong impact on the maturation of source rocks and the generation of oil and gas. That's why I'm considering all this also through time. This will not be my topic today, but what I did here as a model assumption, I assumed largely constant crustal thickness over time. We know that's not quite true. We probably started off with a thinner crust, but for simplicity, I used a constant crustal thickness through time. For the lithosphere asthenosphere boundary temperature, I have 1330 degrees, and the thermal conductivity and radiogenic heat production also assumed constant over time. Because if I only consider the sedimentary phase of that area, which started off around 500 million years before present, it's fairly prudent to make such an assumption of a constant radiogenic heat production and thermal conductivity. Transient effects are considered. Transient effects basically here in our example play a role as we have a continuous stacking up of sedimentary layers and continuous burial with different velocities. We have phases of fast burial and not so fast burial and different lithologies, of course, and all that has impacts like thermal blanketing, for example, which also by itself imposes changes on the surface heat flow. All this is considered and taken into account in the code of the model here. And when it comes to heat transport, heat transport is I exclusively look at heat conduction here. I'm not looking at heat convection processes because the data that we have do not allow me to model localized convective cells or something like that. So just to show you what sort of data I was playing with, I was actually blessed, I have to say, with the amount of data. So on that map, the map you see here in front of you has an approximate acreage of 100,000 square kilometers. And the dots are indicative of exploration wells that have been drilled over the past decades. These are, for this study here, altogether more than 220 wells that I had available. And within these 220 wells, I had more than 750 individual temperature data available. And those temperature values were mostly BHT data, sometimes drill stem test data, sometimes downhole gauge data in wells where we did hydraulic stimulation. I got higher resolution temperature data, but I would say 90% of the database is bottom hole temperature data, which I corrected. All the data you see here are corrected BHT data, corrected either wherever the data and the logging procedure allowed me to do so with the 3 or 4 point Horner correction, or with simply more empirical 1 or 2 point corrections using the circulation time of the boreholes, which was data that I had luckily available. So what you see on the left-hand side now is the blue lines are actually my model outcomes, and the dots obviously the temperature data that I gathered for each of those charts for those individual rectangles that you see on the map. So each rectangle actually gathers together a number of wells, and that's not just chosen by randomly and by without any system. So those are chosen, those rectangles are chosen according to the tectonic regime. So I was always trying to stay within one tectonic province, tectonic unit, or within one terrain and within terrain boundaries, which you see highlighted here. The background, the solid lines are indicative of these deep falls, which are also like the terrain boundaries. So this is just to show you the database that I had available. And the blue line, of course, is the end result of my model calibration and iteration process. So I'm not starting off with this match. So you see here, overall, a very good match between the model outcome and the data. But this is all a result of iterating the thermal parameters and properties that I have shown you on the previous slides for each of those individual tectonic provinces. Now, when I first compiled these data, actually, it was, to be honest, it was a little bit too nice to be true when I saw that. I was completely unbiased when I first looked at that temperature data set. And after correcting all these temperature data and plotting them geographically, georeferenced, you see the map on the left-hand side and all the data here on the right-hand side as a depth plot. You see a very clear clustering of lower geothermal gradients to medium geothermal gradients and higher geothermal gradients as you go. I hope you can see that on the map on the left-hand side. So the blue dots are basically more towards the west of that colored area than the greenish orange dots more in the central part. And the red dots are all clustered, pretty much all of them clustered towards the eastern portion of the study area here. If we translate that into geothermal gradients and into surface heat flows, you see a very nice systematic picture crystallizing out here. Overall, we see a very, very clear, nearly equidistant increase of geothermal gradient from west to east. So in the westernmost portion, we have geothermal gradients of the westernmost portion of 22 degrees per centigrade. So the lowest geothermal gradients in the west, And as we head eastwards, we, as I say, nearly in an equidistant manner, we increase the geothermal gradient from 25, 28, 31, and the maximum I've seen is about 35 degrees per kilometers. So you see, it's not dramatically high geothermal gradients, but the trend, the regional trend, is what is of interest here. That was quite striking. And on the other side of the chart, I labeled the surface heat flows that are also an outcome of the modeling process. So after having achieved the match between measured and corrected bottom hole temperatures and my model outcome, I come to surface heat flows increasing from approximately 47 milliwatt per square meter in the west, very close to the Arabian Shield, which is shaded in gray here, as you see. And these are values. I think those values, those relatively cold values, are the ones that are represented on your nice background picture on that globe that I showed at the very beginning. So, but the whole Arabian plate shows up as cold. As you see, if we go more forensically, if we have enough data, we have a chance to really forensically dive into the data set, we see a very nice structure suddenly coming out with surface heat flows then increasing from the 50s milliwatt per square meter to the 60s. And in the farthest eastern portion, I see heat flow value, surface heat flow of around 70, 72 milliwatt per square meter. Let's have a look again at the crustal structure here. And that's where I want to get at for the conclusion of all this. Why is that thermal structure showing up as it does actually? So from the GravMag data I showed you earlier, we can draw, and this is actually taken from literature. This was published already by Hansen et al. 2007, the bottom picture here. You remember the asymmetry that I showed for the Arabian plate. And the easternmost portion of that plate is what we're looking at here with the picture at the top. And we see a moho, quite an important moho structure. We saw the basement structure, if you remember. The basement deepens very strongly in the eastern part, where the sedimentary pile thickens up to more than 10 kilometers. And at the same time, that's what we got out of gravimetry data, the moho seems to rise up and providing us crustal thicknesses of around 32 kilometers in that area. And so in the central area, in the eastern portion. And as we go back towards the west, I hope you can see my cursor, towards the west, we have, again, a thicker crust, something between 35 and 40 kilometers. And what we also have, this is what I would like to introduce here on top of the crustal structure, is the terrain boundaries that I mentioned before. So we see, if you just look at the upper crust, these were the values that I assigned for the radiogenic heat production of the upper crustal portion, which is labeled here as layer 3. This is the upper crust. So I assumed around 1 microwatt per cubic meter in the westernmost part of the study area, increasing to 2.5 microwatts, and then up to 3 microwatt per cubic meter in the eastern portion. If I do that in combination with the geometry that I show you here, and in combination with the thermal properties that I introduced you at the beginning of the individual layers, this is how I achieve my best fit between the measured and the calculated temperatures. So now, asking for the heat sources, what are the heat sources actually? It's always the question, what is the major heat source that provides us the thermal field? If you look at these pictures here, what I was trying to do, of course, with my assumptions, and there's not many direct measurements available, or radiogenic heat production, not at all, but what I inferred from what I said earlier, and based on that, I was trying to deconvolute the heat flow for the individual for the individual layers. So the left-hand picture here shows you the radiogenic heat production, the heat flow based on radiogenic heat flow production of the sediments, which is on average, or which spans actually from 5 to 15 milliwatts per square meter. This is simply because the thickness of the sedimentary pile is strongly variable. That's why where the sediments are thin, of course, the contribution to heat flow is low. Where the sediments are thick, which is here in the east, the contribution to the surface heat flow is respectively high. Did that for the upper crust and for the mantle and the lower crust as well. So lower crust and mantle together would contribute with 7 to 8 milliwatt per square meter. And the upper crust here, and this was one of the assumptions I made here in this study, the terrain boundary between that western boundary, the western terrain and the eastern basement terrain. Here is where I introduced a jump of the radiogenic heat production between something around 1.5 to 2.5 microwatt per cubic meter to 2.5 to 3 microwatt per cubic meter. And that gives us a differentiation of the radiogenic heat produced surface heat flow between 11 in the west and more than 24 milliwatt per square meter in the eastern portion. So these are basically major, both model assumptions and model outcomes. What is the implication of that? The implication of that is that I assume that different basement terrains, of course, may have different chemical compositions. And the implication of an increasing radiogenic heat production from west to east implies an increasing or a change of the composition from more basic mafic chemistry to a much more felsic composition in the east. So the felsic is proven by very few, I can't show the locations, but there have been 2, 3 deep boreholes that just penetrated a few meters of granite in this eastern portion. So that would fit to this conclusion. We don't know the age of those granites, though, I have to say. But if we go to the shield is very well known, of course, because it's outcropping. The shield has more oceanic or intermediate crustal composition, which is more on the mafic side. So that fits more with the 1 to 1.5 microwatt per cubic meter that I assumed, as opposed to the above 2.5 microwatt per cubic meter in the east. So if I try to depict that here and step by step deconvolute the heat flow signal or the heat flow map that I modeled for the surface, which is my surface heat flow overall across this acreage between 45 and 72 milliwatt per square meter, as I showed you earlier. And then subtracting step by step the radiogenic heat produced by the sediments, the 5 to 15, then the radiogenic heat flow produced by the upper crust, minus the heat flow, the radiogenic heat flow produced from the lower crust, gives us ultimately an inferred, I mean, you understand the assumptions that I made here. I had to make assumptions, but making these assumptions, I get to a so-called background heat flow, or how do you call it? Some people call it reduced heat flow or MOHO heat flow of around 25, 26 milliwatt per square meter, which I believe is in very good accordance with literature values that we know for many parts of terrestrial heat flow regimes. So overall, doing that heat budget calculation here, from a total 100% surface heat flow, we can deconvolute this heat flow system into its components and basically come up with that ratio, the famous ratio of approximately 50-50, or if you wish, 60-40 radiogenic heat from the crust versus background heat flow or primordial heat flow, if you wish, from the Earth interior transported through the mantle. And this 60-40 ratio, as you probably very well know, is something that has been established already in the late 60s by Birch, Lackenbruch, and Pollack, etc. So that is the major that's one of the conclusions for that southern portion of the study area. And here a little bit of a side story as a practical application of all this. Having such a model helps us tremendously, of course, in mapping out temperature, subsurface temperature distribution for all kinds of sedimentary layers that we as a petroleum company routinely map out all the time. So we know where certain aquifers are, we know where certain porous layers are. So we can map them as we have the depth structure of those layers. And I can easily project their temperature distribution on them. And one of the applications here is, you certainly heard about the recent hype around lithium. Lithium may be associated, or extraction of lithium may be associated with convective heat flow systems. So if we take an analogy that we know from Germany, or the Rheingraben system, which has somehow a similar setup. We have a granitic basement in the Rheingraben. It's an extensional regime. It's chopped up by normal faults. And those normal faults are basically conduits of hot waters into the sedimentary pile. And those hot waters also leach out lithium amongst other minerals from the basement and transport them to shallower depth, where they can eventually be exploited commercially. So a similar situation is something that I highlighted here for this Jafurah basin here in Saudi Arabia. We have these bounding faults, as I showed you a couple of times, very deep-seated, high-angle boundary faults, which are penetrating the basement. And those faults, and looking at the temperatures that we have here, you see, I hope you can see the legend. This is a map of the top basement temperatures. So in the deepest portions of the basin, we see temperatures of above 350 degrees centigrades. This is very substantial. And so why not imagining that hot waters are migrating upwards along those fault systems and transport minerals with them. This is something I just show as a side aspect for the practical use of these considerations. This is another layer. This is, for example, the Permian. As we know, also the Permian has been or is still an important hydrocarbon reservoir, but it in some places also acts as an aquifer because it's a porous sandstone system. So we can also map out the temperature distribution of this Permian section here, as we can do for the Triassic and Cretaceous. And you see again very nicely overall the structure of the temperature distribution reflects pretty much one-to-one the structural grain of this area. It's all kind of north-south segmented, and we have high temperatures in the east with cooler temperatures in the west, and the segmentation which is north-south oriented. All right, so I promised you talking about North Arabia as well, and I promised you also to provide a more comprehensive heat flow map for the Arabian Peninsula. So this was the southern part. Now let's move towards the north, an area which we call Nafud Basin. And that Nafud Basin has its border against Syria and Jordan, the northern section of Saudi Arabia. And it's also influenced, as I said at the beginning, with this element here, this northern, pretty much southwest, northeast trending fault system, which is the Dead Sea fault system, the strike-slip system, which is called here Palmyra zone. And associated with those fault systems in this transpressional or transtensional regime are massive basalt extrusions that have given an imprint on the thermal field. So I had a similar database available in that northern section, also about 300 or 400 wells with at least 500, 600 temperature data, which again, we all corrected. PhD data, most of them corrected them. And in a very similar way, I see a segmentation of geothermal gradients as I showed you in the southern portion. Now, this time it's not east-west, now it is it is north-south oriented. You can already gather from that map here, which is representing the surface heat flow map in the northern part. The reddish colors in the north are indicative of these red dots here, or are equivalent to the red dots here on the left-hand chart. And you see again, more or less, if you're generous with me, the higher geothermal gradients are actually clustering around the northern portion of that area here. So it really lends itself to assume that the fault system and that these basalt extrusions have had a very strong imprint on the thermal system, on the thermal field in that area. Whereas if we go back towards the south, towards the interior of the Arabian plate again, to the areas which we have been discussing earlier, which I highlighted as the western portion of this, which, if you remember, were relatively cold thermally. So that fits then quite nicely together, although we don't have data here in the middle. But the heat flows that we find here in the south are in the high 40s, 50s milliwatt per square meter, which are matching very nicely what we see a little bit further south in the plate interior. So this is a composition of the surface heat flow now. Finally, as you see it, we were able to map that out. I did not map the Arabian shield because simply there is no data available. But there's also, on the other hand, no reason to assume that the shield pretty much follows the isolines that we have been mapping out on the I call it Arabian platform. So everything that you see in color here is essentially hosting sedimentary basins and has a thick sedimentary cover on top of our Proterozoic basement. But if you see the colors, it's quite intuitive to assume that as you extend those isolines, you would find a similar thermal regime, say between high 40s and 50 milliwatt per square meter in the shield. And then as you approach the Red Sea, you very quickly get into a totally different thermal regime, which is made up by the Red Sea rift system, which has nothing to do thermally with the Arabian plate interior. I also superimposed here in red and blue lines, which are representing the crustal thickness as they were derived, as I said, from GravMag data and deep seismic reflection data. What you see is essentially a crustal thickness between 32 and 40 kilometers. That doesn't tell us much yet, but what I did here, I plotted the surface heat flow that I modeled for the different areas. So the darker blue is for the eastern portion. The dark blue shaded is the dark blue shading is for the northern Arabian portion that I just showed you, whereas the light shading is representing the eastern portion of the Arabian platform. In both cases, we see a relatively clear trend, which is essentially a decrease of surface heat flow with an increase of crustal thickness. This is a very well established and very well known correlation that we know from worldwide terrestrial heat flow provinces. However, what we can see here on this chart quite nicely, the slope is different. Though the slope is not constant, of course, because we are looking into very different heat flow provinces. We have a heat flow province, which is essentially made up by the, let's say, sediment-dominated Central Arabian platform with very deep basement, structured basement with different composition. That's the heat flow, excuse me. That's the heat flow system in the central part of the crust of the plate. Whereas if we go to the northern part, this slope is much steeper. This is simply because, as opposed to the interior portion of the plate, we have very recent tectonic processes playing a role for the thermal field here and impacting the thermal field. But in both cases, we see the clear trend, just with different slopes. All right, that brings me to my conclusions. So essentially, overall, in the Eastern Arabian plate, we see a strong differentiation of heat flow. So I think we can contribute here with something as opposed to so far known heat flow maps from that area. So we have a systematic and strong structuration of heat flow. Overall values are between 40 and 72 milliwatt per square meter. For different reasons. Tectonics plays a major role in the north, and basement composition plays the major role in the east central part of the Arabian plate. With that, I would like to conclude, and I'm open for questions or remarks